This video is about uncertainty in measurement. When we measure quantities, all of our tools have a degree of uncertainty associated with them. Let's take this measuring cylinder for example. What would this measurement read? We know the exact number is somewhere between this line here, 21 mils, and this line here, 22 mils. But if we're reading this point here, how do we know the exact value? We might say that it is 21.5 mils, but we are uncertain about the third digit in our value. It may also be 21.6, 21.55, or anything between those two lines. This is where significant figures become important. All digits of a measured quantity, including the uncertain one, are called significant figures. A measured mass of 2.2 grams has two significant figures, whereas one reported as 2.2405 has five significant figures. The greater the number of significant figures, the greater the certainty implied for the measurement. Let's compare these two numbers as an example. We have 4.0 grams and 4.00 grams. For most people, these numbers are the same, but for a scientist, 4.0 grams has less significant figures and is therefore less certain. 4.0 has an uncertain value where this 0 is. That means it is plus or minus 0.1 grams. That means the true number could be anywhere between 3.9 grams and 4.1 grams. Our second recorded number, 4.00, has the final digit uncertain, which means it is plus or minus 0.01 grams. The true number could be anywhere between 3.99 grams and 4.01 grams. This second value is clearly more certain than our first value. Here are the significant figure rules. We use these rules to determine the number of significant figures in a reported measurement. First rule, all non-zeros count. Any digit that isn't a zero is a significant number. All captive zeros count. If a zero is between other numbers, it is a significant figure. No leading zeros count. If the zero is before any other number, it is not a significant figure. For trailing zeros, when there is a decimal point involved, such as in these two examples, the zeros are significant figures. In this example, where there is no decimal point, the zeros are not significant figures. So for 3,500, it only has two significant figures. Significant figures in calculations. When carrying measured quantities through calculations, the least certain measurement limits the certainty of the calculated quantity and thereby determines the number of significant figures in the final answer. We will use two rules to keep track of significant figures. For multiplication and division, the result contains the same number of significant figures as the measurement with the fewest significant figures. For addition and subtraction, the result has the same number of decimal places as the measurement with the fewest decimal places. Let's go through a few examples. This first example, the width, length, and height of a small box are 15.5, 27.3, and 5.4 centimeters respectively. Calculate the volume of the box. Let's start by looking at the significant figures of the measurements recorded in this question. This number here has three significant figures. This second one also has three significant figures. This one, however, 5.4, only has two significant figures. This will become relevant when we do the calculation. So the volume formula is length times width times height. Let's put our numbers in. So if we were to type this into the calculator, this is what we would get. 2285.01. Now, this was a multiplication calculation, which requires us to use the lowest number of significant figures in the measured value. Here, we have two significant figures. This is the lowest number out of all of our measured values. That means our answer must have two significant figures. So I'm going to round this so that our number has two significant figures, so we have 2,300 centimeters cubed, and we can rewrite this using scientific notation. So we have 2.3 times 10 to the power of 3 centimeters cubed. Here is another example. A gas at 25 degrees Celsius fills a container whose volume is 1.05 times 10 to the 3 centimeters cubed. The container plus gas has a mass of 837.6 grams. The container, when emptied of all gas, has a mass of 836.2 grams. What is the density of the gas at 25 degrees Celsius? First of all, this is our formula for density. We have density equals mass divided by volume. We have two recorded masses here. We've got 836.2 grams and 837.6 grams. Now, to find the mass of the gas, we need to subtract the mass of the container by itself from the mass of the container plus gas. So the mass of the gas equals 837.6 minus 836.2. This is going to give us 1.4 grams. Now, this was a subtraction, which requires us to look at the smallest number of decimal places in our measurements. Looking at both of our values here, we've got 1 decimal point, 1 decimal point. That means the lowest number of decimal points in our measurements is 1, which means our answer must have 1 decimal point, which it does, so that's fine. We're going to leave it as it is. Now we're going to bring this calculation down. Using this formula again, density equals mass divided by volume. We now have our mass, and our volume is this value here, 1.05 times 10 to the power of 3, and we're going to divide them. Let's see what the calculator gives us. We've got 0.0013333, etc. A very long number. Now, this was a division, which requires us to look at the smallest number of significant figures in our measurements. Here we've got 2 significant figures, and here we've got 1, 2, 3 significant figures. So the smallest number is 2. That means our answer must have 2 significant figures. So we've got 0.0013 grams per centimeters cubed, which we can rewrite as 1.3 times 10 to the negative 3 grams per centimeters cubed.